Good, so let's talk about path integral formulation for master equations. And what I have in mind for now are systems that are considered well mixed, meaning I ignore any kind of space. I just look at reactions. So think of a particle A being born and dying, or two particles interacting in a way that they just show reactions. So that means that n is a vector describing the number of particles in I of type I. That's what I mean. Okay? And I may be A, B, C, etc. Then you know that if you want to determine the time evolution of that is just given by the Q matrix multiplied by the probability vector. Well, it's a silly way of writing this. So here I'm writing here P of t, and here also P of t, and P vector then simply means that I want to have the various states in my system corresponding to the vector n. All right, now, so how do we go here to a path integral? So let's say we start from something like that, P and T, N naught, T naught, and we don't like the fact that we have a discrete variable for the reason I explained to you before the break, and we want something that instead of a discrete variable has a continuous variable. A way of thinking is the following. So imagine, and this is just now my intuition behind the choice that I'm going to make. So imagine you have some kind of volume and you place particles at random in this volume, and you want that this has a certain average x. So the mean number you find in this volume should be x. Because all these events, by placing particles in here, are random, what you expect is that the distribution of particles you find in this volume will be a Poisson distribution. And so you expect that the probability of finding n naught particles in this volume is the mean x to the n naught divided by n naught factorial e to the minus x. This is a Poisson distribution. See? That's what you typically get. Now, let's say we want a marginalized distribution function, p of n and t, that now averages over initial states that are Poisson distributed. So that means I'm writing this as a function of the mean and some time t0, and I'm summing here over all possible realizations of particles in this test volume V from 0 to infinity, and I have here P and T, N naught, T naught, and then I'm averaging over this, which is my Poisson distribution. Okay. And you see what I've gained now? This object, which is marginalized over the initial value being Poisson distributed, is now a function of a real variable instead of a discrete variable n naught, because here I'm talking about the mean of a distribution. This is called, or we call this, a marginalized distribution. Okay, now you may say, what's a special choice that you make here? Do you recover the general solution from that? Well, it's not really a special choice, it's just a transformation. It's transforming this distribution into that distribution that's a function of x instead of a function n naught. And I can always recover that from that by the same construction as I showed you before the break, because in the end this is a generating function. So if you act on this by some differential operator, you will get that back. So what's the differential operator? You can check for yourself, it's elementary math. So if you act on P of n and t, x t0, and you set x to 0, you recover P n t n naught t naught. Now, there's a different way of looking at that, which is helpful later on. So, if you look at that, another way of looking at it is to say this is actually a decomposition of this object here in a vector space, and the vector space is spanned by the Poisson states. So let me define as n x a bra, which is the Poisson states, factorial e to the minus x. So if you do that, then psi defined as p of tau x, which is nothing but this. It's just my bra notation of that object. It's some initial condition or final condition that you have here. Then there's dependence on x, which is now the index, and this is my time t0 that you have here. Okay. So this state here is decomposed into 0 to infinity, probability n naught t naught, n naught of x. Okay. So what we have now is a linear vector space with the eigenvectors being Poisson eigenstates, and the decomposition that you see here. Okay. All right, now that we have that, let us now write down the equation of motion that we want to solve. And it turns out here that the best way, or the shortest way, let's say, to actually solve the equation, okay, let me this way, t0, is to look at the backward master equation. This backward master equation propagates probability backward, so we have minus t0 here, and then the structure that you have in the backward master equation is that we have here nt mt0 q m n0. Okay, and now we multiply that equation, right, with the eigenstates with these basis vectors that we have here, and we sum over n naught. So multiply by n naught x and sum over n naught. And then you get an equivalent equation for this object, okay, which is then q p of x and t0. But now the object, so once you do that projection, once you do that, the operator that you get here is, as in the case of our simple example for the linear depth process, an operator in this new variable, and possibly also in the derivative. Okay? So this will be an operator that depends now on x and also on the derivative of x. We will later, and today I think I don't have the time to do that, explicitly calculate what that operator is here. For now it's just important to know that if I do this, this will be a differential operator. And it will also be normal ordered, meaning that in this operator the dx are all to the right. Q is normal ordered. Okay, so now let me abbreviate that. So let me call this here psi of x and t0, and this here as well. Just a shorthand in the same way, right, as we did this here. This is the psi I'm talking about. Okay? And now, just for your convenience, the notation is such that the argument, which is here as an index, comes as an argument explicitly in the bracket. Okay. So what do you have here? You have a partial differential equation, right? This is a time derivative. This is an operator containing x and dx. So it is a partial differential equation. Very much as a Fokker-Planck equation. Fokker-Planck equation also is just of that form. And if you look back in your notes, the operator there is the operator containing the drift at a diffusion term. Okay? So how can you then rewrite a PDE into a path integral? That's the basic question. And what I show you here works in the same way for the Fokker-Planck equation and for any partial differential equation. Actually, if this object is normal ordered and the differential operator is acting first. So how does that work? Well, let's just rewrite our solution psi of x0 t0. Okay, let me also call this now x0 here. In a way that I solve my PDE in an incremental way. So I take the left-hand side, write it as a difference quotient, and then I take the difference quotient with minus t0. So that means I will have this here minus the corresponding expression at t1. And that's the object I take on the right-hand side. And multiply with a delta t. So this is then q hat x naught dx naught acting on psi x naught t1. Okay. And when I do that, I make errors, but the errors are of the order of delta t squared. So now you have a iterative type of relation. You can relate the object you want to know at time t0 with the object at some later time t1. The operation you have to perform is this differential operator, but you can write this in a funky form, and you see then why this helps. So you can rewrite that as a double integral over q1 x1 2 pi, and now n is just the number of components that we have here, so don't confuse that with the n we have there. It's just really the number of components, so maybe let's call this capital M, and n is the number of components. That's not really an issue here that's important. What's important now is the following. You can write this as 1 plus delta t q hat x naught, and then here complex unit I q1 e to the minus I q1 x1 minus x naught psi of x1 t1. So why does that work? That's just a resolution of the 1 that I have here. So if you, let me help you so you see that. So as an aside, if you take the derivative of a function f naught, then you can write this as an integral over dx1 delta x1 minus x naught f of x1, right? That's kind of trivial that you do this. And then you write the delta function as a integral over phase space factor dx1 dq1 over 2 pi e to the minus I q1 x1 minus x naught f of x1. Right, and once you let that act here on this brings you down ai q1. Yeah?
It's like a Fourier transformation.
Well, in a way, so it's a resolution of the 1.
Which you got by
it's not really a Fourier transformation that I do here. It's really using the fact also that the Q is here normal order, because otherwise you couldn't do this. You need that this object here is acting on this and not acting on that. Because otherwise you would get additional terms from acting on this as well. So it's not quite a Fourier transform, because then you would Fourier transform the variables x naught as well. That's not what I do. So it's really a resolution of the 1. I'm writing this 1 here in a funky way.
Yeah, but we brought in the Fourier modes.
You brought it in a way that looks like Fourier modes. They're not Fourier modes.
I would say that was...
Yeah, I would not call them Fourier modes. They are plane wave terms here. What this will become is our path integral action. Okay? Because once, so if you take that as the resolution of the 1 that you have here, then all I did is to make this once, right, in this iteration scheme. I can repeat that. Of course, I can go on and rewrite this also in a second step. So I can do this a second time, and the fourth time, and so on. So in the end, you get a product running from I equal 1 to n dxi dqi over 2 pi to the n. Then you get an exponent. Oh, I should do this as well here, sorry for that. So let me write this first like so. This is this double integral q1 x1 2 pi to the n. And then because I'm working at order delta t, I can take all of that here into the exponential. So I have here minus I q1 x1 minus x naught plus delta t q hat x naught I q1 bracket closed psi of x1 and t1. Okay, so I can reiterate the whole game because this one here, right, is related now to this one, but psi of x1 t1 is in the same way obeying a relation like so, and so on and so forth. So this is just a recursion relation that I have derived, and I can iterate that recursion relation such that this becomes minus sum over I through n. Then I have IQ I x I minus, that's a complex I here, I minus 1 minus delta 2 t q hat x I minus 1 I q I times the final thing, which is psi of xn tn. So let us look at this here first. Right? This is nothing but an integral over time that we have achieved here. So this is the same as when I write this now in continuous fashion, x of t0 starting at x, then all these discrete integrals, they define then my path integral. And here I do get the exponential of minus the integral from t0 to tn, and tn is actually my t. It's the final point in time. And then I do get I q, then I get d tau x from the first term, and from the second term minus q hat x I q brackets, and this is now my action, so minus s of x and q. So indeed we do have a path integral that we derive from for a mass equation. The only thing left to massage is this object here, but let us write this out as well. This here is a sum over m from 0 to infinity, p of n tn m Tn x n to the m factorial e to the minus xn. This is how my vector in the space of Poisson bases is defined. That here is a conditional probability which is evaluated at the same time points. So it means this must be delta n minus n. And that means that the whole thing that we have here is our Poisson basis for n evaluated at xn, but xn is x of t. This is the value of my continuous variable at the last time point. So that is the path integral that you get in the end, where you say that the probability t of n and t x t0 is given by this expression there. Yeah.
When did we use that we chose this Poisson basis?
Not yet.
Because that was, we could have chosen another one yet for everything we've done right now.
Yeah, you could have chosen this in different ways. Yeah, so it doesn't really matter that much here, because all that I was really using is not fully depending on it, just to the fact that I need to have an operator that's normal ordered. So if it's not normal ordered, I can't do this trick of the resolution of the one.
So in principle, if I have another basis,
yeah,
I get a different Q hat.
Yeah, and that people do that.
Same trick.
Yeah, people do this. Yeah.
I have a different inverse formula with the P of n again to transform the x to the n again, but
yeah. Okay, so I used it here. I used it actually here.
That's the inverse formula.
Yeah, that's the inverse formula.
That
for that expression, and this is discussed in the literature and the lengthy review that I wrote some time ago with a student, where this basis here is a choice you can make. It will turn out that the Poisson basis is a super convenient choice. And that's something I'll show you tomorrow, because in that basis, you can write this Q hat in a very natural way in terms of raising and lowering operators. That's the key point.
And the Q, as you voted, the Q hat as a function of IQ, that's just the multiplication operator now, right?
It's now a multiplication operator because X is a field and Q is a field.
Yeah, that was a derivative, so that
yeah.
was a complicated operator,
So,
not just multiplication.
Recall, right? When we look at this, it's very close in terms of what we write here. There's an IQ here. It's the same kind of field that you have there, because it's representing the action of differential operators. And here that IQ is also having its origin in the differential operators. And I actually invite you as a exercise for yourself, derive this action here using the Fokker-Planck equation, this one, and doing the same steps as I did here. Because this is, again, right, this is a partial differential equation with the operator A, DIAI, DIJ, BIJ is the operator. And you just have to replace Q by that object, and then you get.
Maybe minor difference, because that is like the Fokker-Planck forward equation, and we did the...
No, you will actually need to do the backward equation.
Yeah, but then
because
the operator.
Yeah, the operator here, you see it has a problem. The forward operator in the Fokker-Planck equation is not normal ordered.
But the backward is just the inverse.
Yeah, the backward has the Bij in front.
Yeah.
So it is normal ordered, and then you can make the same trick with the resolution of the one that I've been using here to go through. And then all you have is that instead of Q hat, you have the corresponding backward Fokker-Planck operator, and this is the backward Fokker-Planck operator. See? Okay. You find it also in the notes. It's uploaded there. I've done this
So very
in an earlier version.
We first have a condition on the discrete index. We transform that with a choice of basis to continuous index.
Yeah.
And then we kind of applied regular Fokker-Planck backward logic to it.
Yes.
Okay. And then iterated it.
Yeah. So, or to even broader, any partial differential equation, any one that has a normal order, can be phrased in terms of a path integral. Right? Because that's all I used. Not more than that. What the interesting aspect then is what is that object, Q hat, then, in terms of operators or fields, and how is it related to the Q matrix that we have here. And then you might already anticipate from the example I showed you before the break that the Poisson basis is very convenient, because then all these processes where you create and destroy particles, and that's all there is in Q matrices, have a natural formulation in terms of raising and lowering operators. All right. Thank you.